All right, we're going to go ahead and begin with practice exercise number 18. Practice exercise number 18. You will not need a calculator, but you might want a little bit of extra paper as you work this, practicing with multiplying fractions. Remember, you don't need a common denominator to multiply fractions. You just multiply across, but a couple things. Can you multiply mixed numbers, Lana?
No.
No, you can't multiply mixed numbers. What do you have to do with any mixed numbers you see, Abby? No helper. What do we do with mixed numbers? Josh?
Change them into improper.
Yeah, change those into improper fractions. Then remember, you want to try to cancel things out of numerators and denominators. Never numerator with numerator, but numerator with denominator, often diagonally. And then when you get your answer, since this is not algebra class anymore, we do want to make sure we leave our answers as mixed numbers. So if you're watching on YouTube, go ahead and pause the video, complete practice exercise 18, and we'll go over the answers. All right, let's go and take a look at the answers to practice exercise number 18. Going across the top row, check your work. Should have gotten 7/10, 17 45ths, 8 45ths, and 21 44ths. Going across the next row, we needed to put our whole numbers over 1 to make them fractions, some canceling here, and some improper fractions that need to change back into mixed numbers for answers. For the first one on the next row, should have gotten 2 2/9 when we turn it back into a mixed number. Then for the next one, 7 1/2, then 11 2/3, and for the last one on that top row, should have gotten 22. Middle row going across, your answers are 1, 2, 37 4/5, and 29 1/3. Next to last row going across, your answers are 1 1/9, 2/3, 2 1/6, and 2 7/9. And for the bottom row going across, your answers 8 1/3, 3 2/3, 8 1/15, and the last answer was 13 9/40. Hopefully you did well with that exercise. Again, been working through fractions in the last several exercises, adding fractions, subtracting fractions on the last couple, here multiplying fractions. And if you take a look ahead, the next one will be dividing fractions, and we'll look at that in the next lesson or two. All right, go and set practice exercises aside, and if you would, go and get out your class notes section of your notebook. We were working on a proof. Well, that is to say, we got everything started, never actually did anything with the proof, but go ahead and have that out, and let's pick up where we left off there. As you're getting it out, I want to review some terms with you, or some things with you that we covered in our last lesson. Talked about lines that aren't on a proof starting out. They're not anywhere in the given, they're not in the sketch, but we really need this line to help us finish the proof. What do we call lines that are added to a figure to assist in completing the proof? Josh?
Auxiliary.
Auxiliary lines. What are they called, class? Auxiliary lines. Good. And these auxiliary lines, we used one of them in proving Theorem 3. Theorem 3 said this, that if you have a triangle, and in a triangle, any two sides are equal to each other, what must be true? Got a triangle with two sides equal. Yeah, it's isosceles, but what's true about the triangle, Brandon?
Angles opposite equal sides are equal.
You read well. Angles opposite equal sides are equal. So whatever angle is across from this side, that'd be this angle, will equal the angle that's across from this side, which would be that angle. These two angles would have to be equal to each other. And if that's true, that equal sides dictate equal angles, then we proved that an equilateral triangle, Adam,
Is equiangular?
Is also equiangular. Very good. I would put that down as one of your Clang statements, by the way, that if you have equal sides, you have equal angles. There's not really a place for it, just mentally. Make a mental note of that. That if you got two equal sides in a triangle, Clang, opposite angles equal. We got a lot of Clang statements, right? For instance, perpendicular, class, right angles. Angle bisector, class, two equal angles. You got a midpoint. Two equal segments. You got, felt like there was one more Clang statement. Perpendicular is a Clang word, midpoint's a Clang word, angle bisector is a Clang word. If I think of it later, I'll bring it up. But we also now have as a Clang, two equal sides in a triangle, class, Clang. equal angles across from those equal sides. All right, so for our class notes proof, go ahead and read the statement at the top of the page for us. Brecken?
The bisector of the vertex angle of an isosceles triangle is perpendicular to the base and bisects the base.
All right, so we said the bisector of the vertex angle. So if these are the two equal sides. By the way, what do we call the equal sides, class?
Corresponding. No.
I heard it from someone.
Corresponding.
Legs. Whoever, I think it was somebody over there said legs. The legs are the equal sides of an isosceles triangle. And between the legs, we have the vertex angle. And Brecken said that the bisector of the vertex angle, it kind of, well, actually, this isn't very well drawn at all, is it? But we don't trust our eyes. That's the bisector. Now you say it doesn't look like a bisector. Well, your eyes are wrong, okay? But this will have to be, even if it doesn't look perpendicular, it has to be perpendicular. And not only that, but this line must also bisect the base. So I think we called the triangle, was it ABC? Is that correct? Okay, and then we called this bisector CD, correct? So for our given, tell me what we had down here, Dylan?
Isosceles triangle ABC with AC BC.
All right, pause there for a minute. All right, then what?
CD bisects angle C.
And was that everything in the given?
Yes.
All right, so we're given an isosceles triangle, we're given the bisector. We wanted to prove, and I think there were two things we were proving here. Noah?
CD is perpendicular, or CD perpendicular base, AB.
CD, and you read it correctly the first time. CD is perpendicular to AB. Okay?
And CD bisects AB.
And CD bisects AB. And I believe you already got your two columns set up yesterday. We have to put it back up here on the board now. Statements, reasons. Obviously, your first statement, class, is simply whatever's given, and your first reason is simply the one word, given. All right, and so isosceles triangle ABC with AC equal to BC. Clang! CD bisects angle C. Clang! All right, right off the bat, two clang statements. What should I put for one of my clang responses here, Abby?
Angle, or 1 equals 2.
Okay, and do we number the angles up here at the top already, class?
Yeah.
Oh, okay, so we also did the ones at the bottom. I think there was 1, 2, 3, 4 is how we did that? Okay, so right off the bat, Abby said, what again? Sorry.
Angle 1 equals angle 2.
And your reason.
Definition of angle bisector.
Good. We have two equal angles, definition of angle bisector. Angle 1 equals angle 2. How many were thinking the same thing? That's old clang. There's new clang. I said anytime you're given a triangle and you're given two sides equal, class clang, opposite angles equal. Anytime you got a triangle, class, and two sides are equal, clang, opposite angles equal. Okay, so we're looking at the whole triangle. So try to ignore the existence of this bisector CD for a minute. Just look at the triangle as a whole. This line equals this line. What angle is across from this side right here? Michael?
For what?
What angle is across from this side?
B.
Angle B. Again, ignoring this, angle B is across. And what is across from this side to which this was equal, Michael?
A.
Angle A. So if these two sides are equal, those two angles are equal. How many thinking that as well? That is a clang response. Anytime you see equal sides in a triangle, you got to get equal angles because, read it again for us there, Brandon.
In a triangle, angles opposite equal sides are equal.
In a triangle, angles opposite equal sides are equal. And hopefully we won't have to read that much longer. We'll have that statement memorized, and we'll use it a lot today specifically as we work on memorizing that fact. All right, well, there goes all my clang. I used it up. So now we have to do our analysis. Again, clang means you just know exactly what you're saying before you even think about the proof. But now let's think. I'm trying to prove I have a perpendicular. What would have to be true for CD to be perpendicular to AB? Lana? That's something I'm trying to prove. So somewhere in the proof, toward the bottom, it's going to say that CD is perpendicular to AB. But how? How would I be able to say that it's perpendicular? What would have to be true before I could say that? Do they look perpendicular?
Not really.
Why don't they?
One looks longer.
Longer?
You said CD and AB.
I said, is CD perpendicular to AB? So here's CD, here's AB. Do they look perpendicular to you?
No, one's slanted.
What do you mean slanted?
Like, what?
Well, it's true, You can't trust your eyes. So she can't say it's not perpendicular because it doesn't look it. But the whole point is, something looks perpendicular if it appears that you have... Okay, I was asking Lana, but Brandon... Right angles. That's what perpendicular means. You have to think about what things mean. Perpendicular means right angles. And Lana, the reason you say, well, it says slanted, well, what does slanted mean? Not a right angle, right? Like if this wall were slanted, we'd say, that don't look right. In two senses of the word. And that's the reason why, remember, we call it a right angle, because it looks right, it looks proper, it looks correct. So if these two angles are right angles, then that has to be perpendicular, correct? If indeed they're right angles, that's the key. That's what I was looking for. How many were thinking that? When I said, what would it take to get these lines perpendicular, you were thinking, I got to get two right angles at 3 and 4. Okay? So begs the question, what are right angles? Angles formed by perpendicular lines. Well, there's some circular reasoning for
90
it.
degrees.
No, we don't define in terms of degrees, because degrees are defined in terms of the paragon. So we can't do that, Josh.
Half a straight angle.
We could define it as half a straight angle, that's true. Is there a way to show that 3 and 4 are halves of a straight angle?
I mean, the base is straight.
Okay, so we do know at D we have a complete straight angle, correct? What would it take to show that 3 is half and 4 is half?
Of a straight.
Of a straight angle, yeah. Of the straight angle that's at D. Brecken, help him? Okay, here's the question. If Brecken seems like he's having a bad day, so if we guillotined Brecken, what would it take for us to see that each piece of Brecken was exactly half?
We'd have to
So we're obviously not just sticking his head there, because his head's not that big.
maybe measure.
Well, I mean, if I put it together, I get the whole Brecken, but that's regardless of where I chop you. What would it take to get all? What would it take for me to act? For instance, how many of you have a sibling and there's like a cookie or something? Maybe it's a large, and you're like, okay, we each get half, and you try to break it right here. Anyone ever try to do that? Or have a sibling who does that to you if you're not the oldest? Okay, is that half? Why isn't that half, Brecken?
Because it's not. It's not.
But why not?
Because they're not equal.
Oh, because they're not equal, right? What is the actual technical definition of right angles? Look it up. It's one of the hardest definitions students have every year to remember, but it's an important definition. Go back to your terms definition section. What is a right angle? What are right angles? Dylan, read it for us.
Angles formed when two straight lines meet to form equal adjacent angles.
Angles formed when two straight lines meet. I do have two straight lines meeting to form equal adjacent angles. Now I have two adjacent angles, right? They have a common vertex at D, they have a common side between them. There are two straight lines meeting, but these would have to be equal to each other. So follow the logic here. If these angles are equal, then they are right angles. And if they are right angles, then CD is perpendicular. Does that make sense? So really what I need is I need to find a way to say that angle 3 equals angle 4, don't I? Okay, I need to get two angles equal to each other. What are some ways to get two equal angles? Or what is perhaps the most common way that we use to get equal angles, at least lately? Adam?
CPCTE.
But in order to use CPCTE, I gotta have...
Side, or
What does CPCTE stand for, Adam?
congruent parts, corresponding parts of congruent triangles or equal.
Corresponding parts of what?
Congruent triangles.
Ah, so in order to use CPCTE, I have to have
Corresponding. A congruent triangle.
class congruent triangles. I gotta have some congruent triangles here. If I had congruent triangles, and they don't look congruent, but if they were congruent, then by CPCTE, these would be equal, right? And if they're equal, then by definition, 3 and 4 class are,
Equal.
well, yeah, if they're equal,
Right.
then that makes them right angles. And if they're right angles, I got the perpendicular. Does that make sense? All right, so here's the next question then. If we want to use CPCTE for this, I need congruent triangles. How could I go about trying to get triangles congruent, Abby? Okay, she didn't even list out the methods. She went straight to ASA. What do you see, Abby? We already have it. 1 and 2 equal. There's some angles. A and B down here equal, and in between them, the sides equal. In the given, we have ASA. So number 4, let's state that the two triangles are congruent. Abby, tell me what to write.
Triangle ACD is congruent to triangle BCD.
And the reason you said,
ASA.
and because these two triangles are indeed congruent, that means, Adam, that I can get,
Congruent triangles.
yeah, we just got it. Because we have congruent triangles, Adam, I can get
3 and 4.
to be equal to each other by
CPC.
CPCTE. And since 3 and 4 are equal adjacent angles formed when two straight lines intersected, that makes 3 and 4 what kind of angles? Brecken? Right angles. So number 6, all right, angle 3 and angle 4 are right angles. Reason? I'm not lining up very well here, but reason? How do I know they're right angles? I don't know that I have perpendicular, so I can't use that. But I know that they're equal.
Isn't there two?
Right, and so if two angles are equal, they are right angles?
They're,
No. Oh, Lana.
they're two adjacent ones?
Well, I mean, two adjacent angles. So these are two adjacent angles. If they're equal, does that make them right angles? She's looking it up again. That's a smart move. That's what you do, right? When you're like, wait a second. What is it again? You go back and look it up again. Lana, read it for us again. Nice and loud.
Two angles formed on two straight lines made form equal adjacent.
Ah, here I have 3 straight lines, don't I? So equal adjacent angles is meaningless. But if just 2 straight lines, 1, 2, form equal adjacent angles, then they're right angles. Lana, what did you just read to us? You read us the
The
of
a right angle.
definition of right angle. So based on the definition of a right angle, I know that 3 and 4 are right angles. And if 3 and 4 are right angles, then class, what does that mean? CD is perpendicular to AB. Reason, Josh?
Definition of perpendicular.
Good, lines that form right angles. Since they form right angles, they are perpendicular. That's the definition of perpendicular lines. Definitely learn these definitions. If you're still kind of rusty on them or struggling with them, keep working at them. Okay, you say, well, we're not learning that anymore. No, but we're using it, so you better know them still. All right, one thing down, one to go. I need to prove that CD bisects AB. What does it mean to bisect something? We tried to do this to Brecken a minute ago. Well, okay, not really, just talked about it. We don't really, by the way, Grace Christian School does not endorse guillotining people, for the record. Dylan?
It's a line that divides an angle into 2 equal parts.
If it's an angle bisector, yes, it would divide an angle into 2 equal angles. We're trying to prove that some line bisects some other line. But what does that mean? Michael?
It means that it divides equally.
Divides it equally into 2 equal parts, right? We could argue that would mean that D is the midpoint or whatever, but bisect just means to divide it into 2 equal parts. Dissect means to cut open into however many parts or pieces you need to be able to see stuff, right? Bisect means 2 equal parts, okay? So, I just need 2 equal parts. If I had 2 equal parts, CD comes down, there's a part, there's a part. If those 2 parts were equal, then yeah, CD does bisect AB. What would need to be true to have CD bisect AB? Let me come back to Dylan. AD has to equal BD. Does everyone see that if those 2 things are equal, then regardless of appearance, CD must apparently bisect? Does that make sense? Okay, so here's the question. How can I go about getting AD equal to BD, though? Dylan, trifecta?
Well then, if angle A equals angle B and angle 3 equals angle 4.
I want AD equal to BD. I don't want CD equal to CD. I mean, it's true that CD equals CD, but I don't need CD equal to CD. Michael?
Angle 1 and angle 2 are equal, so they're opposite sides are also.
Oh, be so careful. Be so careful. Let me do this. We would agree that, and again, I know we can't trust our eyes perfectly, but these two angles are almost equal to each other, correct, class? They're pretty much equal. All right? Are these two lines equal to each other? No. Angles or sides opposite equal angles in different triangles doesn't give you equal lines. So just because 1 and 2 are equal doesn't make these segments necessarily equal because they're in separate triangles. But I like the thought, but there's a simpler way. There's a simpler way. Adam?
AD equals BD because CB, CDE.
Yeah, they're congruent, remember? And AD and BD are corresponding parts of the congruent triangles just as much as 3 and 4 were, right? So AD and BD are equal to, let's sneak that into number 5. CPCGE, right? So AD equals BD, that's also CPCGE. And so they're already equal. We just had to write it in. And so if they are equal, then we have therefore a line that divides another line into equal segments. So therefore, number 8, yeah, based on the definition of what a bisector is or does, CD bisects AB. Definition of bisector. And this is not definition of angle bisector now, but definition of bisector. And there we go. So any isosceles triangle, the rest of the year, if you ever have an isosceles triangle, even if it's turned crooked like this, if it's isosceles, and you bisect that angle, boom, you know it's perpendicular, you know it bisects the base, automatically, because we proved it. And that means we could use this in the future. If we happen to see something like this again, we don't gotta go through all these steps again. We've already proven that right there. Questions? Yes, sir.
So what will we say that we proved it for? So
When you prove something, it allows you to use that fact later. It's like in legal proof, right? Everything that's decided or ruled on gives you now something you can use in a ruling later. So yep, it's just another tool in the toolbox. It's just like every other theorem, every correlation. It's just a tool in the toolbox we can use to prove other things. All right, go and take out another piece of paper. This doesn't necessarily have to go in the notebook. You can if you want to. So I will say, I would caution you against putting too much in class notes, as it can clutter the most important stuff. So that's my only thought. If you put everything in class notes, you lose track of which things are important and which things aren't. And it takes the study value of your notebook away from you. All right, but on your paper, go ahead and draw another isosceles triangle. Draw another isosceles triangle. And let's see here. Let's go to Brandon. Do you want to go tall, skinny, short, squatty? What do you want to do?
let's do short squat.
Short, squatty. It is. All right, short, squatty triangle. If you already drew tall, skinny on your paper, you don't have to redo it. I'm just going with what we're going to show on the chalkboard, by the way. And let's name it BAF. Or maybe it's a fab triangle. No, it's definitely not fab. It's just BAF, whatever that means. All right, and we've got our two equal sides, right? It's isosceles, so we got our two equal sides. That'll be in the given here. So we're given triangle BAF with BF equal to AF. You like fab better? Yeah, you know, sorry. This way it goes in life. Now, I want you to pick some point on BF, anywhere you want, and we're going to we'll just kind of make this Brandon's triangle, so to speak. Brandon, where do you want to put your point? Closer to B or closer to F? Because I want to avoid the midpoint, lest we think something's true that isn't.
Closer to B.
Closer to B. So we'll pick a point maybe down here. Let's look about good right about here. Okay, so pick a random point down around B. And let's just call this point X. Now, here's what I want you to do. Whatever the distance is from B, I want you to figure approximately on the picture, because the sketch doesn't have to be perfect, but approximately that same distance from A, plot a point in that same position on the other line. And let's call this point Y. So we've got a little piece here, BX, and a little piece here, AY. And those two little pieces are going to be equal to each other. So we're given that BX equals AY. Now, if you would, locate the midpoint of AB to the best of your ability. Again, it doesn't have to be perfect because we don't trust our eyes. Call it M for midpoint. And we'll put that in the given, that M is the midpoint of AB. And if you would, I want you to draw lines from X and Y coming back to M. Lines coming back from X and Y back to M. All right, here's what I want to prove. Two things. First of all, I want to prove that fx equals fy. Second of all, I want us to prove that triangle BXM is congruent to triangle AYM. Triangle BXM is congruent to triangle AYM. Once you have that down, 2 columns, statements, reasons. Once you have that down, 2 columns, statements, and reasons. Go and copy down your first statement and your first reason. Let's look at what we're trying to prove here. First of all, we're trying to prove that fx equals fy. Now, if you're not careful, you'll already see fx marked as being equal, but remember, that line is there from when we said that bf and af were equal. So I'm going to do this. You don't necessarily have to do that on your paper, just so we are clear. We don't necessarily know that these two pieces are equal. We know that this whole line bf equals this whole line af. Thoughts, though, on what that must mean? Bless you. As we try to get fx and fy equal. Adam?
Bm is equal to am.
Okay, there we go. Sorry, I just skipped right over the Klein. Yeah, we got a midpoint, so we can say bm equals am. I guess we should take care of, sorry, we should go ahead and take care of the Klein first reason.
Definition of a midpoint.
For that matter, there's another Klein, somebody else. There's another Klein. I'm sorry? Well, that's given that, oh, I'm sorry, you're saying, yeah. The fact that you've got 2 equal sides in a triangle, what's the Klein response to that, Brandon?
The equal opposite. It's not isosceles, but.
Somebody help? He's right, that is a Klein statement. You're given a triangle with 2 equal sides. Klein, Abby?
Equals opposite of equal sides.
Yeah, in a triangle, angles opposite equal sides are equal. Now again, this is in the big triangle, so we gotta kind of tune out the noise going on in the middle here. What angles, back to Brandon, have to be equal? Yeah, angle A is across from BF, and angle B is across from AF. So those 2 angles are equal. Angle A equals angle B, and how did you word that reason again, Abby?
In a triangle, equals opposite equal sides equal.
In a triangle, angles opposite equal sides are equal. All right, and I'll go ahead and mark those little pieces as being equal from the Klein. I think that's it for the Klein. Coming back to what we're trying to prove here. Since I got ahead of myself a minute ago, rewind. Okay, how do I get fx and fy equal? I know that the whole line BF equals the whole line AF. I just want a part of it, xf, equal to another part, yf. Dylan?
Well, if bx equals ay, that subtracted from the whole is equal.
Oh, so if I were to subtract equal parts away from equals, I'd be left with equal remainders, right? Now there's actually 3 steps to this, and I want you to mark these in the proof here. First of all, it's just like with the addition action. Remember we practiced this yesterday, we had a couple parts equal, we had a couple more parts equal, so you're going to want to start by saying the whole equals the sum of its parts. Let's do the same thing here. Let's state number 4, that the whole BF equals BX and XF, and the whole AF equals the parts AY and YF. And the reason we know that BF equals these 2 parts added together, and AF equals these 2 parts added together, class, is because we know that
The sum is, no, the whole is equals to the sum of all.
there we go. The whole equals the sum of all its parts. I'm going to be lazy. I'm just going to write whole equals sum of parts. Just because I'm too lazy to write the whole is equal to the sum of all its parts. I know. All right. And then once we've stated that, because we're given that the whole things are equal, I can take what BF equals and put it right there. I can take what AF equals and put it right there. That's just a substitution. What would I get if I took this, put it in place of BF, took this sum, put it in place of AF? What would that say now, Josh?
BF equals.
If I took this and just went, put it right there. Okay, Josh, BF is or equals BX plus XF. And we know a quantity can be substituted for its equal in any process. So I'm just going to take that, I'm going to put it right in that spot. So I write, literally, instead of BF, I write, no, instead of BF, I write class BX plus XF. I'm literally just taking that and putting it right in that spot. And then it says equals, so I write equals, but then instead of writing AF, I'm going to come back to Josh. Instead of writing AF, I write what AF equals. So what do I write right here?
AY plus Y.
There we go. Good. All that is a substitution, right? And that'll be my reason. But since in the given, we were given that BX equals AY. Well, here's a BX on this side. Here's an AY on that side. What can I do with these 2 equal quantities, class? Subtract them away. And if I subtract it away from each side, what's going to be left? XF equals YF. And that's using the subtraction axiom. I'm just going to write the word subtraction. That's if equals are subtracted from equals, the remainders are equal. Notice the 3 steps. Whole is equal to the sum of all its parts. Then we substitute the parts in for the whole and subtract away to be left with what we want. So it's kind of the reverse of what we did yesterday. If we had equal pieces and we want to get wholes equal, okay, whole equals sum of parts, state the addition axiom, substitute in. If you have the wholes equal and you want to get parts equal, start with the whole equals sum of parts still, make your substitution, then subtract away what you want. So it's kind of a 3-step process, getting fx and fy, or xf and yf, equal to each other. So that's the first thing I wanted. Second thing I want to get some triangles congruent down here. Shouldn't have checked it off yet. I want this triangle equal to that triangle. Thoughts on how I can get those triangles congruent? Reckon?
Side angle side.
Okay, so let's see. What sides or angles do we already have?
XB and BM.
Okay, so this is a side and this is a side. What are they equal to, though?
YA
Is equal to BX.
and MA.
MA is equal to BM. Okay, so we got a couple sides equal here, a couple sides equal here. So all we really need is a couple of angles, but we got those 2 now, don't we? So we've already got by, there we go, number 7. We've already got the triangles congruent. We did that by making our Klein statements. Triangle BXM is congruent to triangle AYM by side angle side. You know, we were able to prove both things there. Questions on this, but especially on this whole equal sum of parts substitution subtraction thing. A process of getting individual pieces equal. If we know poles are equal and other parts are equal. Questions? All right. Flip the paper over or get out a new sheet of paper, depending on what your paper situation is. And let's see, we did a short, squatty isosceles triangle. Let's do a tall, skinny isosceles triangle this time. Let's make a tall, skinny isosceles triangle on your paper. And let's see, Noah, I need 3 letters for this.
X. B. C.
All right. And so we're going to have our 2 equal legs. So it'll be XC and BC. So let's be given isosceles triangle XBC with XC equal to BC. Now, question, can these 2 angles be right angles?
No.
Why not?
You wouldn't have a triangle.
You wouldn't have a triangle, would you? They must be what kind of angles? They must be acute angles, correct? So if that's true, if they have to be acute angles, then I could come right here and I could make a right angle, couldn't I? I want you to make a right angle and come up some certain amount, however high up you want to go. I'll just go that far. Make a little right angle there at X, come up some certain distance. And let's call this point here, Noah, M. It's just wherever you choose to stop. So X, I mean, you go really high, you go shorter, whatever. Draw a line XM so that MX is perpendicular to XB. We want to do the same thing at the end of B. I want you to go straight up, but I want you to do it the same amount you did before, okay? So, and Noah, for this, we'll call this letter N. All right? So we've also got NB perpendicular to XB. So we have a pair of perpendiculars here. But drawn in such a way that they're equal height perpendiculars. So MX equals NB. Once you got that, I want you to connect M to your vertex C and N to your vertex C. So you have this funny looking figure. Now again, your triangle can be however tall or squatty you want it to be, as skinny or as wide as you want it to be. Your perpendiculars can be as tall as you want them to be, but it doesn't matter how you drew it. If indeed you have an isosceles triangle with perpendiculars on the ends of the base that are equal length perpendiculars, we're going to prove that the triangles that are formed out here are congruent. I want to prove that triangle, let's see, we'll call the one MCX. And we'll say that we want to prove it's congruent. What would correspond to the M, class? The N is in a matching position. What would correspond to the C? C. And what would correspond to the X? B. So not NBC, but NCB. All right, once you got that down, 2 columns. Statements, reasons. Once you got that down, 2 columns. Statements and reasons.
Just looking at it.
Question?
I was just saying, just looking at it, I know how.
All right. Get you your first statement, first reason. Isosceles triangle XBC with XC equal to BC, MX perpendicular to XB, and B perpendicular to XB, and MX equal to NB. Now, right off the bat, class, as we have this figure, I see a lot of little angles all over the place. I told you if you got a lot of little angles, especially multiple angles at a vertex, I recommended you number them. So let's start up here. I've got this little tiny angle 1. I've got the bigger angle 2, which was the original angle C, and I've got this little angle 3. You realize if you referred to angle C at this point, it would be MCN that you are referring to. right? Because that's the whole angle. So this way we can refer to individual parts if we wanted. Come down here, we've got this little angle 4, 5, 6, and then 7 right here. I don't need to label the angles at M and N because there's only one angle at M, only one angle at N. All right. Clang and clang. All right, Dylan, you're up. You said you got it, so here we go. This is your moment to shine. Just don't go so fast the rest can't keep up. Okay. There's a clang statement. Okay, right, so. Says what? Oh my, it does? Perpendicular line is a line that divides something into two equal parts?
No, two lines that meet to form right.
Oh, two lines that meet to form right angles. Okay, so, since you have perpendiculars, we're having technical difficulties. This flight is grounded. All right, Brecken, help him fly. Or maybe we'll just all board Brecken's plane and fly with Brecken now.
Angle B and angle X are right.
Good, the angle X, which is the whole angle at X, correct? And angle B, this entire angle at B, they're right angles. Angle X and angle B are right angles. Reason? There you go. Now, Dylan, you told me the definition of perpendicular lines, right? You said they're lines that meet to form right angles. Okay, so since they're perpendicular, we have right angles. Does that make sense? That's what I was trying to get you to go to. All right, Brecken, we're going to fly with you now. I got right angles. I got perpendiculars, right angles. Okay, there's still another clang out there. The opposite angles of what?
Equal sides.
Which two equal sides?
C, B, and CX.
Good. The angles opposite these two sides. Ignore the noise going on outside. Just focus on the original triangle, XBC. Equal sides. I got equal angles. Which angles are the equal ones, Brecken?
Angle 5 and angle 6.
Angle 5 and angle 6. There we go. Okay, so number 3 clang is angle 5 equals angle 6 because, Brecken?
Angles opposite equal sides are equal.
One little clarification. Angles opposite equal sides in a triangle are equal. Right, that's true in a triangle, that if you have equal sides, the opposite angles will be equal. All right? That takes care of all the clang. Now let's think about what we're trying to prove. I'm trying to prove a couple triangles congruent, right? Which two triangles are we trying to prove congruent again here, Brecken?
Triangle MCX.
All right, so that's this little slivery thing right here on the side, and
Triangle NCB.
all right, and that's also a little slivery on the side, right? I want those two triangles congruent. Thoughts on how I could get that?
Side, angle, side.
Or
Angle, side, angle.
or
Leg, angle.
all right, now the latter two ways, class, leg, angle, those can only be used for right triangles. Do I have right triangles? Well, we have perpendiculars and right angles, don't we? But are they in these triangles, though? No. Okay, so even though we have reason to believe, bless you, that there are right angles present, we don't have right triangles still. All right, so now we look, okay, what do we already have? As far as side angle, Brecken, what do we already have?
XN is equal to NB, or
Okay.
BN.
There we go. XM and BN are a pair of sides that are already equal to each other. So we've got a pair of sides that takes care of either one of those, all right?
XC is equal to BC.
Okay, and then right here, XC equal to right here, BC. So there's another pair of sides. Okay, that narrows it down. Which way do I want to use?
Side
I definitely want to go with side angle side. I've already got two sides, so forget angle side angle. Why would I do the hard way? I just need some angles equal. Which angles have to be equal, Brecken, for these two triangles to be congruent?
Angle 4 and angle 7 have to be.
How many thinking the same thing he was saying? I've got to get somehow this angle at 4 equal to that angle at 7. If I do it, that's side angle side. Proof's done. So, Brecken, how do I get 4 and 7 to be equal?
Angle 4 and angle 5 added together equal a right angle.
Okay, let's state that. Let's state what he said. Angle 4 plus angle 5 equals what right angle specifically?
X.
Angle x. How do we know angle 4 plus angle 5 equals angle x, class? We know we have a right angle because of perpendicular. How do I know that 4 plus 5 equals x, class? Definition of complementary. It says something about complementary in my proof.
I like that, yeah.
The whole is equal to the sum of all its parts. Or, as I like to say, whole equals sum of parts. All right. Now, Brecken, I cut you off. Sorry. So you said 4 and 5 add up to a right angle, they add up to x, okay? I think you were going to say something else too, though, weren't you? Kind of along those same lines, perhaps?
Angle 7 and angle 6 add up to a right angle.
Well, specifically,
Angle B.
yeah, angle 7 and angle 6 add up to angle B because, again, the whole is equal to the sum of all its parts. Or 6 and 7. He said 7 and 6 in that order, so I wrote them down like that. All right, so thoughts now, Brecken. You're on a roll here.
Angle 4 equals angle 7
How do we know?
because angle 5 equals angle 6.
Okay.
And
He says he knows 4 and 7 are equal because 5 and 6 are equal.
equals subtracted from equal.
So because Dylan and Brandon they're not actually equal, but let's just say they're roughly equal. Because they're equal, we're equal? Because they're equal? No. Just as two other things are equal doesn't make them equal.
They add angle 4 and angle 5 add up to a right angle.
Uh-huh.
And
Angle x, yep.
Angle 7 and angle 6 add up to a right angle.
Angle b, yep.
Angle 5 and 6 are equal.
Uh-huh.
If they're equal,
Yeah, he's right there. He's right there. You're close. Brandon, can you help him?
Well, my thought was, we have the first state that angle x equals angle b.
Okay, so what Brecken was missing, this is where I was hoping to kind of guide you to, that only matters if these two angles are equal to each other. But they are equal because, Brandon, let's write this angle x equals angle b because, Brandon,
Definition of right angle.
oh, careful. The definition of right angle says the angles forming two straight lines meet to form equal adjacent angles. That would show they're equal if they were adjacent and formed by only two straight lines.
Alright.
We don't got that.
All right angles are
All right angles are equal, though. Yeah, there we go. We said they were right angles in number 2, so all right angles are equal. So, Brecken, coming back to you, since 4 plus 5 equals x, and since 7 plus 6 equals b, then right here where it says x, I could go,
angle 4 plus angle 5,
and right here where it says angle b, I could go
angle 7 plus angle 6.
with or without the sound effects. And the reason their class is simply substitution. And now, Brecken, what can I do with these two angles you keep coming back to? Well, these are equal. What can I do with these two angles you keep saying? Well, they're equal. You'd be like, well, 5 and 6 are equal. Yeah, they are. Take them out. What's the mathy word for take them out, class? Subtract them. If I subtract those equals away, then yes, we're left with 4 equal to 7 by subtraction. And now, since we have 4 and 7 equal, class, we do indeed have congruent triangles by Side angle side. Was anyone thinking real quick of another way to get to that exact same point?
You could say angle X and angle B are equal for the all right angles are equal for point 4, and then you could say angle 4 equals angle 7 because the comps of equal angles are equal.
Okay, close. You'd want to say angle 4 and angle 5 are complementary. Angle 6 and angle 7 are complementary. Then you could say complements of equal angles. That was the direction I was hoping somebody might go, is the complements, but you'd have to state they're complementary first.
Yeah, the way.
Before you can say complements are equal, but that would have worked also. Gets us to the same point of 4 equaling 7. All right, good job. Homework for this evening is to do handout 6. So Gavin, handout 6 from that collection of first semester geometry handouts. The rest of you get it handed to you. All right. And once you've got your handout, you are dismissed. Have a wonderful rest of your day.